Here in this example, we have a disk P, which is able to slide on a smooth horizontal table. Attached to this disk is a cord. The cord's attached to ground back there at point O. And what we know is the cord begins unstretched. And since it's a cord, it can't be compressed, so it's just slack. And it's also given an initial speed of Vp1. Its velocity is lined up with a 36.87 degree angle relative to the line that connects O and P. We know the stiffness of the cord, so once the cord goes taut, it will stretch. And what we want to find out is the velocity vector for P once P's moved out to a distance of 1.5 meters from O, and it begins at a distance of 0.4. And the unstretched length of the cord is 0.6. Okay, so let's look at an FBD of our disk. As we look at this disk from the top, the table is smooth, so there's no friction. Normal force and weight that's perpendicular to the screen, so we can't see those. The only force that's going to be acting on this disk is the force due to the cord. It acts directly toward point O. Or, if the cord isn't even taut, there is no force. So the conclusion is either there's no force or there's a force that acts through O. In either case, if there's a force or not, that does not cause a moment about O. That's what we look for when we are trying to find if angular momentum is conserved, is find a point through which all the forces act. So in this case, O was the point. So it said that if I find an expression for the angular velocity, angular momentum before, that's going to be exactly what the angular momentum is at position 2. That all came from the FBD. I'm going to resolve things in terms of the unit vectors ER and E theta that are shown in the figure. I'm going to redraw them here from the top view as this. And from this we see that HO1. HO1 by definition is R cross MV. R is referenced back to point O, VP1. So the position vector for P is the distance R, R1, in the ER. VP1. Well, VP1, we need to project this velocity here onto ER in E theta. So its projection there on ER is going to be VP1 times cosine of 36.87. And its projection on E theta direction is going to be that speed VP1 sine 36.87 in the E theta direction, like that. So again, we're just using the definition for H, and along the way we need to resolve the initial velocity in terms of ER and E theta. Whenever I cross R with V, I recognize, as always, ER cross with itself is a 0. So then I have M, the radial distance R1, the speed VP1, and the sine of 36.87. It just came from the R cross MV, and that ER cross E theta is a K. So that's what H was at the start. HO2, R cross MV, same thing, except we're doing this for time 2. So the R vector is this distance R2, ER. crossed with VP1 or VP2. Don't know either the radial or the transverse component, so I'm just going to write this out as an R2 dot ER. That's the usual polar description. R2 omega 2 E theta. ER cross with itself, that's a 0. So that's good for us because we don't have to know what R dot is in order to use this equation. So I have an M R2 squared omega 2 K. So setting H1 equal to H2, I have M R VP1 sine of 36.87 is equal to M R2 squared omega 2. So what we have from this is the theta component of the rotation rate, the angular velocity, if you will, of that chord at that position. The m's cancel out like this, and we get R1, we know that, VP1, we're given that, sine of 36.87, divided by R2 squared. So again, this is the angular velocity of that chord. It's pinned to ground there at O, so that's the angular velocity of that the chord sweeps out on the table as the disk is moving there at position 2. What we're asked to find is the total of velocity, not just the angular of velocity. Back here, when we felt good about this, we said R2 dot, which is what we need to know. We felt good because we didn't have to know it in order to solve this equation because it just didn't appear. ER cross with ER is a 0. But now we're stuck with the task of finding them. Well, one thing that we can observe is that not only is angular momentum conserved, but energy is conserved. As we look at the forces that's acting on the puck, the only force that's acting is that chord. The chord is a spring that can stretch. So energy is conserved. So when we write down T1 plus V1, that's equal to T2 plus V2. The chord is initially not stretched, so there's no potential in there. T1 is 1/2 mv1 squared. The second position, 1/2 mv2 squared. And 1/2 k delta squared. Delta 2, or delta here, is equal to the length of that chord, R2, minus the unstretched length, R0, which, when we look at it, it says here the unstretched length is 0.6. So we know delta, like this. So since we know V1, we can solve for V2, where V2 is going to be V1 squared minus K over M delta squared square root. Well, this is getting us in the right direction here. We were looking for the velocity vector. We know one component, we know R omega, and now we know the speed, the magnitude. So the good thing about this is that the velocity as a vector, that's R dot ER plus R2 omega 2 E theta. And if we take the magnitude squared of both sides, at this point we see that we know this. We just found that. That's the speed. We know R2, that's given. Omega 2 we found from angular momentum. So from this equation we can solve for R dot R dot's going to be the square root of V2 squared minus R2 omega 2 squared. Again, we know all of this on the right hand side, so we now know R dot, and therefore we can write the velocity vector V2 in terms of the now known R dot, ER, plus R omega, E theta. That's what we were asked to find. Let's think back, let's go back and see what we had to think about in order to get that answer. Well, the first step was to look at an FBD of this disk. And the observation here, the key one, is we found a point O that the forces acting on the disk always either doesn't exist or it passes through O. So the moment is a zero about O. So that tells us that angular momentum about O is a constant. We find out what it is at the beginning. We know the initial velocity, we get the radial position vector, and we get this for H1. H2, we don't know that, but we write down V in terms of its polar coordinates, which cross R cross MV, and we get this. Those two are equal, and that's how we got omega 2. We were looking for the vector. That's only one part of one component. We still need to find R dot. Couldn't find that from angular momentum. You never can. But the good thing here is that we know that energy is conserved as well as angular momentum. So the initial kinetic energy is this, the final is this, the change in potential is due to the stretch of that cord, and so that gave us an expression for V2. We use the magnitude of velocity to find R dot, and then from that we can find the velocity vector V2.